graph smiles or frowns, calculus can tell you exactly why. What is concavity? Concavity describes the shape of a graph and is determined using the second derivative. Understanding concavity helps us analyze how functions curve and change direction. A graph could be concave up, that is, it would look like a smile and open upward like a cup, or a graph could be concave down. It would look like a frown and open downward like a cap. If f of x is a function, the second derivative tells us everything about concavity. If the second derivative is positive, the graph will be concave up on that interval. And if the second derivative is negative, the graph would be concave down. Here are the steps to find concavity. First, calculate the first derivative from the original function. Then calculate the second derivative by differentiating the first derivative. Then, find the possible points of inflection by solving the second derivative be equal to 0, or find the points where the second derivative is undefined. Finally, use a sign chart to determine concavity on each interval. What is a point of inflection, you may ask? A point of inflection occurs where concavity changes and the function is defined at that point. It's important to note that the point where the second derivative equal to 0 alone does not guarantee an inflection point. The concavity must actually change on either side of that point. So think of it as the moment when the graph transitions from smiling to frowning or vice versa. So if we look at this graph here, it goes from concave down to concave up. So this point here would be a point of inflection. Let's see how all of this applies through some examples. In this first example, given the cubic function f of x equals x cubed, in order to find concavity, we'll need to first find the first derivative. F prime of x will be equal to 3x squared. And from the first derivative, we can find the second derivative. F2 prime of x will be equal to 6x. In order to find the points of inflections, we'll let the second derivative be equal to 0. And solving for x, x will be equal to 0. So that will give us two intervals, from negative infinity to 0 and 0 to positive infinity. For points where x is negative, the second derivative will also be negative. Therefore, the function will be concave down on that interval. And for x positive, the second derivative will also be positive, and therefore, the graph will be concave up on that interval. So since the graph will go from concave down to concave up, the point x equals 0 will be a point of inflection. In this second example, given the quadratic function f of x equals 2x squared minus 4x plus 1, in order to identify concavity, we'll first find the first derivative. F prime of x will be equal to 4x minus 4, and the second derivative will be equal to simply 4. Since the second derivative is always positive, the parabola opens upward across its entire domain. In other words, the graph is concave up everywhere. In this case, there are no inflection points because concavity never changes. In this third example, we have a rational function f of x equals 1 over x. So in order to find the first derivative using the power rule, we can rewrite 1 over x as x to the power negative 1. We can find the first derivative to be negative 1 over x squared, and the second derivative to be 2 over x cubed. Now we know that the second derivative will be undefined when x equals 0 because we have x cubed in the denominator. So that will give us two intervals, from negative infinity to 0 and from 0 to positive infinity. For negative values of x, this will be negative, and therefore the function will be concave down on that interval. For positive values of x, the second derivative will be positive, and therefore the graph will be concave up on that interval. It's important to note that the point x equals 0 is not in the domain of the function. So even though concavity changes, we have a concave down function from negative infinity to 0 and a concave up function from 0 to positive infinity, there is no inflection point. Here's your challenge for today. Find the intervals of concavity and any inflection points for the function f of x equals x to the power 4 minus 4x squared. First, find the first derivative, find the second derivative, find critical points for concavity, and test each interval. You now understand how to analyze concavity using the second derivative, identify points of inflections, and apply these concepts to various functions. If concavity finally clicked, please like and subscribe. And don't forget, math success starts when you stay on the fast track. Thanks for watching.